write a program to add up all the odd integers. And we wrote that program, and I'm going to quickly write that on the board because I need to build on it. The program to add up all the odd numbers, begins with the odd number stored in a variable. So I need a variable int n equal to first odd number 1. And I also need a variable sum set to 0. Since I'm going to add to sum, I have to have a value to begin with. And that's all I need. I can come back and add more variable if I need. So I need to say, it says add all the odd numbers from 1 through 30. So n starts at 1 and it has to go up to 30. So while n is less than or equal to 30, sum equal to sum plus n. So right after adding n, you need to change n to go to the next one. You had to do both inside the loop. So I need curly bracket because I'm writing more than one statement. And to go to the next odd number, I just have to add 2. So n equal to n plus 2 and close that. And that will add up all the odd numbers. So when the loop finishes, we can see out the sum. Okay, now, if I want to add reciprocals of the odd numbers like this, 1 over 1, 1 over 3, 1 over 5, all the way to 1 over 30, then all I have to do is, instead of n, where do I have n? I need to say add 1 over n. So just write the reciprocal n there, 1 over n. But then since you're dividing integer by integer, you need to make one of them float so that it'll be, and then also sum has to be float now. So float sum equal to 0 because these numbers you're adding are now fractional. So you need to have float type variable. Okay, so instead of these odd numbers, let's say I want to add up 1 over 1 squared. Even though 1 over 1 squared equal to 1, I want to keep the pattern. 1 over 3 squared plus 1 over 5 squared. If I want to add up these, all I need to do is go back to the program, and 1 over n now changes to 1 over n times n, the square in parentheses. So now it's adding up squares of those. So it's even though sometimes the series may look complicated, but the program is very simple. It's pretty much the same kind of program. Always add whatever you need to add to the sum, put it back in sum, and then change the n afterwards right here. I'm changing to the next. And there's always a pattern on the n, so change the n after adding the current term. These are called the terms. Each one of these is called the terms. So after adding each term, change the term to go to the next, and then close the loop. That's about all you need to do. All right, so let's see. I already went over that. This one is, okay, write a program to add up to the squares of the odd numbers. I already went over that. So let's see, next warm-up exercise. I want you to write this program. Let's start with the first one. Actually, we just did that first one. Yeah, I just did. You see on the board right now the program. That's the program to add up 1/3 squared and so on. The 1 is same as 1 over 1 squared. So let me explain something here. You could I'm going back to the board. The sum, the very first term is 1. And so we don't need to compute 1 over 1 squared. If you do that, it's not a big deal. But if you don't want to do that, you can start sum at 1. So let me go back and let me erase that sum here. Sum, I can start the sum at 1. Then the n will also change. So sum equal to 1, that means I'm holding the very first number, this number, in sum. And so n should start at the very first number, the very next number, 3. N should be 3 to add 1/3 squared, n equal to 3. And the rest of the program will be same. So now sum initially has a 1, and then I'm adding 1 over 3 squared to it. And then n changes to 5. And then loop continues to add up all of these. So you can start sum at 1 of the very first term. If there is no need to, if you don't want to compute that, then you can start with that first term stored in the sum. All right, so now let's see. Warm-up exercise 2. That's the one I want you to do now. Put it in the chat. Oops, sorry. Either put it in the chat, or if you handwrite it, then you have to show it to me by putting it against the camera.
Professor, can you check if you got my email, please?
Check email.
Yes, from Sam, to see if you got my email.
I don't want to.
Oh, I understand. It's fine. Okay.
Yeah,
I'll just talk with you
out of this.
to make sure.
I have the setup all for the class, and I don't want to get out of that.
Yeah, I understand. Okay, well, I sent you the email right now. So thank you, Professor. I appreciate it.
Yeah.
I sent you email as well.
Okay. I need all of you to write this program. Warm-up exercise 2. There's no program in the chat. No one is writing. Okay, let's see. I have a program from Terence, but it's not correct. You can see that the denominator is not 2 times 5, 3 times 5, and so on. Denominator is powers of 5. So what you are adding up is 2 times 5, 3 times 5, and 4 times 5, and so on. That's not correct. And also to add things up, you need to create a third variable. And that variable should be on both sides, like I did on the board here. Sum equal to sum plus, and that sum has to start at some value. And then to the sum, you add this, put it back in sum. Only then you're adding up. That's the only way.
Can I ask a question?
Yeah.
What's the condition here for our loop?
What?
What's the condition for loop like? Like, for example, in homework exercise, we had like sum supposed to be less than sum than 4, or what here should I?
Okay, yeah. In the previous one, okay, I understand your question. In the previous problem, we stopped the n goes from 3 to 30, so we were able to control the loop by the n going up to 30. So here, the power of 5, the denominator is powers of 5, and so 5 squared, 5 to the third, all the way to 5 to the 20. And we cannot write 5 to the 20 in C++, right? 5 to the power 20. That's your question, right? Okay. That is correct. You cannot control it by the value in the denominator. So you're going to have to control it by another variable you can introduce to keep track of the power. So when you're at 1/5, your variable power will have 1. When you get to 1/5 squared, the power will be 2. So the power will have to keep going up. And when the power is 20, you're done. Understand? So you're going to have to keep track of the power in a second variable and controlled by that variable. All right, Ivan, you got it?
Yes, thank you, sir.
All right, I see some programs now. So Terrence, Bob, you need to rework on that. Program is not correct. And there are 4 text messages, so let me take a look. That's Terrence, Bob. All right, I have one from Simran. I don't know, in times. And okay, Simran, what you're doing is you're adding up 1/5 squared plus 1/6 squared plus 1/7 squared. That's what you're doing. Okay. Also, you don't write n equal to n plus plus. You just write n plus plus semicolon. Just n plus plus semicolon. And you're increasing n. So that means you're adding up 1/5 squared, 1/6 squared, 1/7 squared, and so on. That's not what we need. Okay, let's see. See one from Alexander. Power of 5 times 5 n plus n is 1. Right. Alexander has it right. Very good. Okay, Christopher, let's say equal to 20. No, Christopher, you have in the denominator 1/n times num, where n is changing from 1 to 20, I see that. So basically you're doing 1 over 5 times 1 first, and then 5 times, and then 6 times. See, you're changing num. So 5 times 1 and 5 times 2, 5 times 3. So that's what you're adding. 1 over 5 times 1, and then 1 over 5 times 2, 1 over 5 times 3, all the way to 1 over 5 times 20. It's not 5 times 20 we need 5 to the power 20. So that's not quite right. You're adding the wrong series. Okay, B less, David back. While B less than or equal to 30, B times B. B doesn't have any value to begin with. You're saying int equal to B? What is that? That's incorrect C++ statement. I think you meant to say int B and equal to some value. You had to have some value for B to begin with. So no, that's not correct program. All right, I'm looking at Ivan's program, sum equal to 0, num equal to 5, denominator. Num times num means you're doing 5 squared. And then what is that plus 1? Did you mean to have all of that in the denominator, or you're adding 1 more to the whole? You're actually adding 1 to the whole thing by putting a plus 1 there. If you want
But
that,
in conditionals is one adding to whole thing.
yeah.
Like,
The denominator having num times num plus 1 is not adding up powers of 5, right? That's 5 times. You need parentheses in the denominator. Even if you put parentheses, your denominator is 5 times 5 plus 1, and that's not 5 squared. So no, that's incorrect. Keep trying.
sir, but adding will be separate from uh, division.
From
Like first will be denominator will be divided to num multiply on num, but adding will be separate. It's not going to denominator to numerator.
No, what I'm saying is, you don't have parentheses, so the denominator, which is 1, will be divided by 5, okay? And then the whole thing will be multiplied by another 5. You see that? Your statement is incorrect. If you wanted num times num in the denominator, then you need parentheses around it. Otherwise, what you have here is 1 over 5, the whole quantity times 5, which is equal to 1. Okay, so num is 5. So the very first thing you're adding is 1 over 5 times 5 plus 1. This is what you're adding to sum. You didn't want that, right? So you need parentheses around the num times num if you wanted num squared, 1 over num squared. Like I have here, parentheses around n times n, you need that parentheses. Otherwise, you're not squaring.
Thank you.
But it's incorrect anyway, because we don't need 5 squared and then num times 1. Num is multiplied by 1. How does that help? Num is not changing at all. Num star equal to 1 means num equal to num times 1, and that means multiply num by 1. That's not changing num. So num is not changing here, and so this loop is infinite. I'm looking at second version of David Back's program, B times B. Okay, now you're adding 1 over 5 squared again and again. The b is not changing. So you're adding 1 over 5 squared over and over. The b is 5, so a is 1. So 1 over 5 squared is added to a. You don't even have 1 over. This the statement is wrong. This a equal to a plus b times b, a plus slash. I think you meant to write a plus 1 over b times b. The 1 is missing. But it's still, that's not adding up our series. You're adding 1 over 5 squared over and over. Okay, I'm looking at Anissa program. Sum plus equal to 1 over pow times equal to 5 n plus plus. Right. Anissa has the right program. You haven't indented everything in the while loop. You need to indent them, otherwise it's correct. Okay.
Thank you.
Mhm. All right, let me, only 2 students have the right program. So let me clear the screen and explain that. Well, that's disappointing. Only 2 students managed to write it. No one else wrote it. That's not good enough, but I'll show you how to write that. We need to begin the sum. We can begin the sum at 1. So float sum equal to 1. And same float type variable n equal to 5. The very first denominator is 5. So that's what I'm storing in n. And then we know that loop, we need the loop to add up. So while something is true, let's introduce pow to hold the power. Right now I have 5, so it's same as 5 to the 1. So power will be 1. And when I change 5 to 5 squared, I'll change the power to 2 and so on. So while we'll come back to the condition later, inside the while loop, I need to add 1 over n. N is 5 right now, so 1 over n. So sum equal to sum plus 1 over n. So the n has to be a variable because I'm going to change the n to go to the next term as soon as I'm done with adding this. So sum equal to sum plus 1 over n. And after that, I need to change the n. So look at the n. How does it change? From the first term is 1 over 5. For the next term, the denominator is 1 over 5 squared. For the next one, 1 over 5 cubed. So that means I need to multiply the current value of n by another 5 to get to the other one. You can see that each one is 5 times the previous one. So n equal to n times 5. That's how I generate the next one. I also need to keep track of the power to control the loop. So therefore, I need to increment the power here so that power keeps track of the power. All right, so close the loop there, and that'll do it. Patrick B. As you can see, n is initially 5, and to the sum, I'm adding 1 over 5, and then n changes to 5 squared right there. And power becomes 2 to keep track of the power. And with the 5 squared, I go back to the top. If the condition is true, then I'm adding 1 over 5 squared. N has already changed to 5 squared. So I'm adding 105 squared to the current sum, putting back in sum, and then n changes to 5 cubed, tau changes to 3, and going back. And if the condition is true, I'm adding 105 cubed. So it keeps going. So to control the loop, I am using tau. So what's the condition now? Anybody?
Power less than or equal to 20, right?
Right, tau less than or equal to 20. So that's all there is. All right, moving on. Write a program using loop to multiply the numbers 1, 2, 3, 4, all the way to 20. So 1, 2, 3, 4, all the way to 20. Now we need to multiply them. So that means we need to have a variable prod initially set to 1, and then we keep multiplying prod by these numbers. That's how you accumulate. Just like the sum accumulated the sum of many things, the product can accumulate product of many things by simply multiplying new number to the product. So you had to keep multiplying the product by the new number and store it back in product. That's the only way to generate product of many things. So I'm doing it on the board. I'm going to use the variable n to int n equal to 2. The very first number is 2. I'm going to start my prod at 1. So very first number I need to multiply is 2. Comma prod equal to 1. And then well, clearly we can see that n has to go up to 20. So n is going to control the loop, n less than or equal to 20. Simply prod equal to prod times n. So n is 2 right now. So I'm multiplying prod by 2 and putting it back in prod. So that means prod was 1 before, prod now has 1 times 2. It has 1 times 2. And then the n has to change. So here n is just incrementing by 1. That means I can just put plus plus right behind this. I don't have to write a separate statement. And that'll be it. The loop finishes right there. And when this loop ends, I'll have the product. So I'm going to explain how that product works. See how prod after the loop. So let me explain how that loop works. Initially, n was 2, and 2 multiplied prod, 2 times prod goes back in prod. So the prod is now 1 times 2. Right after that, n changes to 3. So here's the variable n. N was 2, now it changes to 3. And with n equal to 3, I go up and check this condition and then multiply by 3. So now prod has 1 times 2 times 3. And n changes to 4. And go back to the top condition of the loop, and n less than 20 is true. So I'm multiplying by 3. And I'm multiplying the current value of prod by 4. So current value of prod is this. I'm multiplying by 4 and putting it back in prod. And then n changes to 5. And so you can see that it is multiplying all those numbers all the way to 20. When n is 20, it will multiply. And then n becomes 21. When n is 21, the loop ends. Loop ends when n is 21, but all the numbers have been multiplied. All right. I have already done that. So here's a warm-up exercise. All right, let me see if you can write this. The first program, I want to see the program. You need to compute the product of numbers 5, 10, 15, all the way to 100.
Sir, in example which you showed, what you declare with n? And what is it in the beginning? 2 or 0? What is it?
I'm sorry, what's the question? N is
What?
starts 2. N is 2.
Okay, thank you.
Yeah. Sorry about my pen. It doesn't always work well. I'm waiting for the program for warm-up exercise 1. Okay, I see one solution. No. No, I don't have any. Too many of you are not writing anything. You need to try and write the program. You can see the pattern. The pattern is the number starts at 5 and then goes to 10 and then 15. So that increments by 5 from starting at 5 and going up by 5. That's the pattern. So you have to take advantage of the pattern. Okay, there are some chats. Let me take a look. While n less than or equal to 100, prod times n plus plus. I'm looking at Christopher's program. It's prod equal to prod times n plus plus. That's incrementing n by 1. Clearly, that's not going to generate the numbers we need.
Yeah, I forgot to increase it by 5.
Yeah. I'm looking at Sam's program.
What's it called? That one's wrong, Professor. My updated one is at the very bottom, where you can get to it later.
All right. Okay. I'm looking at Alexander's while n less than or equal to 25 times 5. Alexander, you need to switch those two statements. The prod times equal to 5 has to go first. You need to multiply the current number and then change the number. You're doing them in the wrong order. So by doing them in the wrong order, everything is going to go wrong. The loop control has to change and so many other things have to change to make it work. Instead, if you just switch those statements, it'll work right. You have a value in 5s, so you need to multiply that to the prod, then change the 5. But other than that, your program is pretty much right. So that's the main thing you need to change. Okay, I'm looking at Anissa's program, n equal to 5, prod times n, and changes. Okay, so you have the whole thing in that for statement. There's no body for the loop, so you need a semicolon behind the for. Behind that for statement, you need a semicolon, Anissa. So if you put that semicolon, it is right. Very good.
Okie dokie. Thank you again.
Shimran, you're incrementing n by 1, and that means from 5 to 6 to 7. You know, that's not the right pattern. Oh, wait. Prod times n. Yeah, n is initially 2 and then changes to 3. No, this is not, that's not even close, because that's not, we're multiplying 5, 10, 15, and so on. You're multiplying 2, 3, 4, and so on. That's not right. Okay, I'm looking at Sam's new version, and equal, let's equal to 100, and equal to plus 5, prod times n. That's it, right, you got it. Sam has it right. Jonathan. N times equal to n means n equal to n times n. If you generate n equal to n times, I'm talking to Jonathan, when initially n is 5, so it looks like 5, changing n to 5 times 5, so that looks right. But in the next step, you're multiplying 5 squared by 5 squared to get the new one. That's not right. So n equal to n times n is not the right way. N equal to n, prod equal to n times n plus 5. Nope, Ivan, that's not right. You're repeatedly, you're not even accumulating the products. You had to have prod equal to prod times something. That's the only way to accumulate products. What you're doing is, you're doing 5 times 10. You're multiplying 5 times 10 over and over. The same multiplication over and over. That's what you're doing. Okay, I'm looking at Terence. A less than equal to 100, B equal to B times A equal to A plus 5. Right, you got it. Terence got it right. Okay, that's good. This time I have 3 students with the right program. Okay, well, at least that's better than 2. But, you know, how come all of you are writing the program right in your homework, but you're not writing them here?
I think you just need time to think about it. You know, of course we will make mistakes, but then we run it.
Yeah, but
You know,
I've been
Yeah,
waiting.
in the homework we get time to think about it. And everyone depends. Like we sit down and we like analyze our own work and we reread it. Here we're kinda on a time crunch to make sure we get it done for you in time.
Right, yeah, I understand. Okay, but yeah, I can't give you too much time, so I understand. Yeah, some of you need to think a little more. Okay, so that's this part 1 of the of section 4.5. Section 4.5 was divided into 2 parts. So I'm going to close this and go on to the next part, which is, again, still accumulation of sums and products, but we're going to go into some other kinds of accumulations we have to do. So let's first understand this operator. Now it was, you probably already have read this because this was used in the last homework problems. So basically, you know, it's x plus equal to y is another way to write x equal to x plus y, because this is now going to be happening very commonly. sum equal to sum plus something, and prod equal to prod times n. We have been writing that. So that's to simplify those, we can write x plus equal to y. So this operator was introduced just to simplify this. It's not a huge simplification, but it does have some advantages in certain situations. So similar to plus operator, plus equal operator, there's also star equal to, and all the operators have these this version. So here they are. X plus equal to y means x equal to x plus y. X minus equal to y means x equal to x minus y. X star equal to y means x equal to x times y. Similarly, we have slash, even modulus. So for all the operators, you have this. Now, when it comes to order of precedence, let me explain something. If I write something like x equal to y times z plus k, whatever the expression is, always there are order of precedences for these operators. So the multiplication will be done first, and then the addition will be done. Only after that, the assignment will be done. The value will be stored in x only at the end. So everything on the right side will be executed, calculated, and then this assignment is the last step. So even if I have x plus equal to y times z plus k, still it's an assignment. Basically, I'm computing all this and adding that to x. So x plus that will be stored in x. So x equal to x plus equal to, this means x equal to x plus that. So x plus y, this is what it means. So it'll calculate that, add it to x, and put it in x. Anyway, this assignment is the last step. So whether it's equal or plus equal, that's the last step. Everything, all other operators will be done before that. So that's why in this order of precedence, you can see that parentheses is first, and then plus plus minus minus, and then multiplication, division, and modulus go next. And if there are more than one of those, it'll go from left to right, and then finally plus and minus. And then the less or less equal, those operators will be next, the comparisons. And equal, not equal will be the next. And then final step will be these arithmetic operators, arithmetic assignment operators. Just like assignment is the last, arithmetic assignment will be also last. All other operations will be done before that. Okay, so let's see. Let's go to the next problem. Write a program to compute the sum of 2 squared and all the way to 2 to the 10. We did one very similar to this earlier. To control the loop, we cannot use 2 to the 10. So that's why we need to have a counter or variable keeping track of the power. And we can only control the loop by the power. But other than that, it's similar, very similar to the one we did earlier. So I'll quickly go over that. Okay, so the variable, I need a sum. They're all integers, so int sum equal to 0 and n equal to 2. Then the n is the very first number, and then after adding the number, I will change the n to go to the next. I also need a counter to keep track of the power. So right now, my first term, n is 2 right now, which is the same as 2 to the power 1, so power is 1. The power is keeping track of the power. Only when the n changes to 2 squared, power will change to 2. Okay, so while we'll come back to the loop control. I need to say sum equal to sum plus. So I'll write sum plus equal to n, simply n. Do not try to change the n right here. That will, if it is a plus plus, if you're incrementing n, you can do the plus plus here. But if you're doing anything else, do not try to do it in the same step. Separately, on the next line, I need to change n. So always begin with the addition, add the current number, then change the number to go to the next. Okay, can somebody tell me how do I change the n?
N plus plus.
Then n will be going up by 1. That's not right. N is
Oh, sorry. N times equals 2.
right. N equal to n times. I'm going to write it as n equal to n times 2. You can see the numbers from 2 to 2 squared or 2 squared to 2 cubed. All I have to do is multiply by a 2. So that's what I'm doing. N equal to n times 2, semicolon. And power has to increase. When the power of n increases, right after multiplying n by 2, clearly power has to increase. So increment the power. And that's it. Loop control is going to be power less than or equal to 10. And that will add up those numbers.
Professor, it says sum plus equal, that's n, right?
And yeah. I'm using Apple Pencil, they're supposed to be the best in the market, but it doesn't always work perfectly. So sometimes it messes things up. All right.
Microsoft Whiteboard is pretty good too.
Whiteboard.
Yeah, by Microsoft.
Okay, I'll try that.
Just check it out. Yeah, just check it out. It's pretty good.
Check it out. Yeah.
Yeah.
All right, we went over that. Let's look at this program. 1 over 2 plus 1 over 2 times 3, 2 times 3 times 4. So the denominator is growing all the way to 2 times 3, all the way to 10, the product from 2 to 10. So, okay, it may look complicated, but program is fairly easy. I'm going to show you why. Let's clear the screen. If you figure out exactly how to generate everything, then the program will be very easy, very simple. The denominator is changing, clearly. How is it changing? The numerator is not changing at all. So we don't have to keep track of the numerator. It's always 1. Denominator is initially just 2, and then it has to become 2 times 3, and then 2 times 3 times 4. But notice that from first denominator to the second one, all I need is multiply by 3, right? If I multiply by 3 from first, if I multiply the first denominator by 3, I'm getting the next one. If I multiply that one by 4, I'm getting the next one. So I have to just multiply by a number, and that number has to change, has to increment by 1. The multiplier has to increment by 1. Can you see that? From first term to second term, the multiplier is 3. From second term to third term, multiplier is 4, right? And from this to the next, multiplier will be 5. So the multiplier changes. That's the only thing you need to realize here. Okay, so I will use the denominator, the variable, the 2 can be in n. I can put it in n, or I'll call it denominator. So everything is going to be float because these are fractional. So float denominator equal to 2, den equal to 2, and then sum equal to 0. And m is my multiplier. I'm going to start multiplier at 3. Clearly, that's the first multiplier, first value of the multiplier. From first denominator to second denominator, my multiplier is going to be 3. So that's all I need. And let me start the loop. And so while something is true, I need to add the fraction to the denominator, to the sum. So sum equal to sum plus 1 over, the numerator is always 1, so I don't need a variable. 1 over the denominator, then. Right after that, the denominator has to change to have 2 times 3. So all I have to do is multiply the current denominator by my multiplier. So can you see that it's now 2 times 3? And then I need to change the multiplier so that next time through the loop, I will be multiplying by 4. So m plus plus. Right after multiplying by current m, my m changes. And that's it. Close the loop, and that'll add up. So as you can see, even though the series looks complicated, it's in fact, the program is as easy as the previous one. Nothing more complicated in the program. Only thing is you have to change the things in the right way. So my m is going to be the control, loop control. You can see that, right? Multiplier from first to the second was 3. From second to third, multiplier is 4. The last multiplier has to be 10. And when I'm finished with 10, when I'm done with 10, the sum is done. So while m is less than or equal to 10, because when m is equal to 10, I do need to do this. When m is 10, I do need to multiply the denominator. No, I do need to add that 1 over denominator. And then denominator changes to another one. I'm sorry, yeah, when the denominator changes here, m will become 10, and that number, that denominator needs to be added. So therefore, when m becomes 10, I still need to add, and then m changes to 11, that's when I don't need to add anymore. So that's why it's less than or equal to 10. So this will add up that series. Even though the series looks complicated, the program is as simple as the previous one. All the programs are going to be as simple as this. You just have to figure out how to change those things correctly. All right, so let me move on. I went over that on the board. So still the same thing. All right, I have warm-up exercise. Write a program.
Sorry, could you go back one? I just want to take a photo of the equation from the previous one slide.
Oh, this program?
Yes.
Okay.
Okay, thank you.
Yeah. You know that all these are available to you on the website, right? The entire.
The PowerPoints?
Yeah.
Oh, I completely missed that. I'll check that.
All the PowerPoint lectures are there, class by class. It's all there.
Yeah, the videos I've seen. Yeah.
Videos are there, and the PowerPoint lectures are also there.
Okay, thank you.
Okay, so we have this program as warm-up exercise. So let me see if you can write that. Write a program to determine how many of these terms have to be added up to get the sum to go over 1.6. You have to first identify the pattern and then take advantage of the pattern to generate the numbers. So the program is almost always exactly like this, what I have on the board. Only thing is the way denominator changes will be different for each problem. Other than that, it's almost always about the same pattern, same structure. All right, I'm waiting to see if anybody gives me an answer. Okay, I see some solutions. All right, I'm looking at Alexander's. Sum less equal to 1.6, sum plus equal to 10 plus equal to 3. Very good. That's good program there. I'm looking at sum plus equal to, and denominator changes, count plus plus. Yeah, one thing is missing in Alexander's program is the counter. We need to count how many things are being added up to go over 1.6. So introduce a counter, then.
Yeah, I see it. Let me correct it.
And Sam has the correct program. Very good. I'm looking at Terence. 1 over b times b increases by 3. Right. Terence has the right program. You need a counter though. You're missing the counter because we need to count how many terms are being added to go over 1.6. And that's it. Okay, so, all right, 3 students had it right. Very good. You have one? All right, I'm going to go over it. Okay, yeah, that's Alexander's new version with the count. Right, very good. Okay, so three.
I submitted one as well, just so you know.
All right. Okay, I'm looking at Shimran's Euler cycle to 1/6. It is correct. Shimran, you have the correct program, except you need a bracket because you have 3 statements in the loop. You need all of them in the loop. You need brackets around them. And then what you need to print is not prod, you need to print the counter, not the product. According to the problem, you only need the count. Okay, so on the board, I'm going over my own version. While whatever, we'll come back to the loop control. I need to add to the sum. So sum equal to sum plus. N is 1, I need 1 over n squared added to sum. So 1 over n times n will be added to sum. I declared my n as float so that this division will work right. So right after doing that, I need to change the n. And as you can see that n is going up by 3. From 1 to 4 and then 4 to 7, it's going up by 3. So n equal to n plus 3 is all I need to change the n. After adding the current, after using the current n, change the n on the next line. Now I also need to count. So increment my counter right there. Counter was set to 0. Now I increment it. So the counter will count how many terms are being added. And the loop control this time is the sum, because according to the problem, we need to determine how many terms need to be added for the sum to go over 1.6. So we need to say while sum is under 1.6, keep going. So that when the sum is over 1.6, loop will terminate. And when the loop terminates, we need to see out the count. The count has the number of terms added up for the sum to go over 1.6. So that's our conclusion. All right, going on to next series. We wrote this already. So, but this time it's not, denominator is not going up to 10. It's, we need to determine how many terms should be added up to get a series accurate to 5 decimal digits. All right, so I don't have to write that program again. We wrote that. What we need to understand now is how do we control the loop if we need to get the sum accurate to 5 decimal digits. Okay, I'm going to explain that on the board. Accurate to 5 decimal digit means, you know, your sum is, when the sum is something like, let's say sum is something like this. 1.5632 let's say this is what I have now, and my next term in this series, I'm going to use this example, the one I just did, to illustrate this. My terms are 1 over n squared. So it's going to, I'm adding up 1 over 1 squared, no, 1 over, yeah, it was 1 squared, and now, and then 1 over 4 squared, 1 over 7 squared, I'm adding them up. But as you can see, that this number is decreasing. The term I'm adding is decreasing. It was 1 over 1 squared, which is equal to 1. And then 1 over 3 squared is 1 over 9, small, much smaller number than the first one. And 1 over 7 squared is even smaller because 7 squared is 49. So 1 over 49 is a very small number. And if you look at the next one, that's even smaller. So they're growing smaller and smaller. So if my sum has reached this, and my next term, I'm computing these terms. These are my terms. The next term is 0.0000023, something like that, then we don't have to add this term anymore. We don't already have 5 decimal accuracy because this one has 5 zeros. 5 zeros means adding this is not going to change our answer. Our answer is already accurate to 5 decimal digits. That's what it means. So when your term is smaller, small enough to have 6 zeros, even if this is a 2, it may change. It may change one of these digits. But if that's also 0, then it's not going to change. So if you want 5 decimal digit accuracy, then you need to make sure your term is bigger than this, 6 zeros and 5. As long as term is, if the term is smaller than this, then you need to stop. We don't need to add that. So that's how you get, you make sure you get 5 decimal accuracy. So I'm going to change my program, this program I wrote earlier. I'm going to change that to incorporate this rule, the 5 decimal accuracy. So let's go back and make the changes to this program. Let me just rewrite it. That will be the best way. I'm going to rewrite this program because now the rule is different. The rule is I need 5 decimal accuracy. It's not, I'm not counting the terms to go for the sum to go over 1.6. This time I'm calculating the sum of the series. It's an infinite series now, but I need 5 decimal accuracy means I will stop after I have 5 decimal digit accuracy. So here is how it goes. I need to introduce a variable term in my program. Term, so float, oops, get the pencil. Float term. Because I have to, in the previous version of the program, I didn't have to store the term anywhere. I just add it to the sum. But now I have to compute the term and store it because term is going to control my loop. So while the pencil sometimes fails. Okay. I'll come back to the loop control. Inside, I need to do term equal to, I need to separately calculate the term now. Term equal to 1 over n times n, n squared in parentheses. And then I'm changing my n equal to n plus 3. I don't need a counter anymore. In the last version of the program, we needed the counter, but here we just change the n to go to the next term, and basically close. So I'm calculating 1 over 1 squared. I'm adding 1 over, sorry, sum equal to, I had to do the sum. I missed the sum. I stored this term. In the previous version, I didn't have to store the term. I added the term to the sum, but this time I need to store it. So let's do sum equal to sum plus term. And then n has to change to get ready for the next loop, next iteration of the loop, n equal to n plus 3. Okay, now I'm controlling the loop by saying this, because what we need to do here is we need to keep adding these terms as long as they're big enough, because we need 5 decimal digit accuracy. So what I need to say in the control, loop control, is the loop control is going to be term. So I need to say while term is greater than 0.0000605. While it is bigger than this, I'll keep adding. When it becomes, as you can see, the terms are going smaller and smaller. So at some point, the term will be too small. It'll be smaller than this. And that's when adding it is not going to change 5 digits in the answer. The 5 digits will remain the same when you add terms that are smaller than this. So that's why while term is bigger than this, keep adding. And when the term is smaller, it'll stop. And when the loop stops, we will see out the sum. That's how you get the 5-digit accuracy. It's an infinite series, and you had to stop somewhere. And according to the problem, you need to stop when your terms are too small. Okay, moving on to.
Professor, is this value the 0.000005, like the regularly used value? Is this what we should be setting our terms to?
Use if the program is asking for 5 decimal accuracy. I
see. Okay.
5 decimal accuracy. It means your answer should be accurate to 5 decimal digits. Means when the term is smaller than this number, the 5 decimal digits will not change, right? By adding the term.
Sure. Would you ask for accuracy to different than 5 decimal digits?
Yes.
And we'll have to change the term as well.
You'll have to change the number. Yes. For example,
okay.
if the problem says we need 6 decimal digit accuracy, then you want to have 7 zeros in your number here.
Okay, I see.
All right.
Mm-hmm.